Hello and welcome to today's video. In this video, we're going to talk about approximation of functions through their derivatives. In particular, we are going to focus on the tangent of a graph first. If you recall the definition of the derivative and differentiation, then the motivation basically was that we wanted to have the slope of a function. And we did that by first defining a line through 2 points on the graph and then moving those points closer together so that finally we would get a tangent. And now in this section, in this chapter, we are going to look at the function that defines that tangent and how exactly it is related to the derivative. So this section is called Tangents for Function Graphs. As I said, the task is to use that slope information to actually express the tangent in the form of an explicit function. So here's our task. We know that f prime at a point x star is the slope of the graph of f at x star. So the question is, how can we express the tangent? And we'll call that tangent t with an index x star. So that's a tangent to f at the point x star. And want an explicit description of that tangent right now. Now let's first make a little sketch to see how this looks like. So the coordinate system. Here's x. Let's say we have a graph of a function that maybe looks like this. So that is our function f. And we also have a point x star. Let's say this here is our point x star. And then of course we can have a look at the corresponding point on the function graph, which is here. And we can also identify the value of the function at that point. So this here is f at x star. Now the tangent at that point would look like this. So that is the tangent t x star that we are looking for. And we want a functional description of that tangent here. So first thing we're going to look at is representing t x star as a function. The function is then naturally a function defined on R, or at least some interval where the function f is defined, and it also maps to R. That functional description would be of the form t x star of x is, well, we already know the slope of that function is going to be f prime at x star. So usually an affine linear function, as we want one, the tangent is an affine linear function, of course, that has the form slope times x plus some constant. So we have something of the form f prime of x star times x plus a constant b. And how can we find out that constant b? Well, of course, we just have to use a point, and we know one point on the graph and on the tangent, that is this one here. So we do know the point x star and f of x star. So with the information that tx star at the point x star has exactly the same value as the function at that point, f of x star, because it passes through that point here, we can easily use that and substitute it into the functional description of our tangent, this here, to obtain f prime at x star times x star plus b is then equal to f at the point x star. So solving this for b immediately yields b is f of x star minus f prime of x star times x star. So ultimately, the description that we get from this is our tangent tx star at the point x can be written in the following form, that is f prime at the point x star. And you notice we have f prime at the point x star times x here. And we also get a minus f prime x star times x star here. So we can combine this into f prime of x star times x minus x star. And then we're still missing this term here, so plus f of x star. So this is the functional term that describes this tangent here, and you can clearly see that at the point x star, this term here becomes 0. So that part vanishes, and we only left with this part. So at x star, the function value is exactly this here. So this is a quite convenient way of writing down that representation here. Now, of course, we also know tangents from linear algebra, and we usually wrote those in a different way in linear algebra. So we're going to explore that as well. Now, having this representation as a function, we also like to have the representation of that tangent in the linear algebra way. And in terms of linear algebra, that tangent is an affine subspace. So that is what we're going to explore here. The representation of an affine subspace. So let's just call this subspace capital T. And that means if we look at that drawing here once again, what used to be our function is now the subspace that we're looking at. And that subspace is characterized usually by a linear subspace, and then a translation of that linear subspace. Let's see how we can describe that. So first thing you'll notice is that T is, of course, closely related to that Tx star that we just had. It's exactly the graph of Tx star. And that graph can easily be written as the set of pairs x and Tx star of x, where x is in the reals. And now we just need to modify that a little to get a nice description of an affine subspace. In particular, we can use the functional description of Tx star that we have just found. And remember that functional description was f prime at x star times x minus x star plus f of x star. For the first element of that vector, we still have our x. And for reasons that will become clear in just a second, we're going to modify that a little. We're going to subtract x star and then add x star back. So in effect, we're adding 0. So this is just for the sake of a nicer representation in the end. X in R. And now what we can do is we can split this term up into a constant part and a part that still relies on x. And we're doing just that now. So that constant part, well, x star is surely constant, so put that in here. And for the second coordinate, we'll take the f of x star as the constant part. And then we have that x minus x star left here. And here in the second part, we have f prime at x star times x minus x star. So what do we get? Well, as you can see, we can factor out x minus x star here. And of course, as x varies throughout the reals, x minus x star also varies throughout the reals. So the next logical step would be to keep that constant part here and then add something like x minus x star, 1, and f prime of x star, like this. Again, x in R. And as I said, this here is just a factor that varies through all the reals. So this here, all multiples of that vector here, that is in effect a linear subspace. So we can write it in the alternative form, where we keep that translation here outside of the set. So that is the translation vector. And then we just add the span of this vector 1 and f prime of x star. And that is, of course, the classical form of writing an affine subspace. You have a linear subspace here and a constant translation vector, right? So this here is a linear subspace. And this is a translation vector. So that is an affine subspace. And that's just the way we wanted it. Let's have a look at the graph and see where we can see those elements here. Now, of course, the translation vector, that is easy to see. That corresponds to this point here. So if you wanted to have that as a vector, that would be something like this. Yeah, so this is the translation vector given by x star and f of x star. Now about that vector here, 1 and f prime of x star, where can we find that? Well, that's also easy to see. If we take that point here and then move to the right by 1, then of course moving up by f prime of x star will simply take us exactly to the point on that tangent here, because f prime is the slope of that tangent. So that vector here is in effect this vector here. Yeah, that is the vector given by 1 and f prime at the point x star. So that's the direction of the tangent, and that is exactly, of course, what you would expect. That direction, and you have a point where the tangent is anchored, and of course a good choice for that point would be exactly this point here. So this gives us a nice description of the tangent of a function graph, either in this form as an affine subspace or in the form of a functional description, which is probably more suitable for calculus. Now, having a tangent to the graph is kind of the first step in approximating a graph. And of course you can ask, can we do better by maybe not using a tangent, but maybe other functions? And of course, one possible choice here would be to substitute that tangent, or to extend that tangent, by terms of higher order. So you could argue we have a constant term, we have a term that depends on x. What about if we add a term that depended on x squared? And that is exactly what we're going to dive into in one of the upcoming videos when we talk about approximation through polynomials. And as usual, I hope I'll see you then.